Hey everyone, welcome back to physics. This will be lecture 7 of the course, and in this section we're going to begin our sort of big section 2, and the section 2 is going to be concerned with motion in 2 or 3 dimensions. So we just finished up discussing motion in 1 dimension, or motion along a straight line, and now what we want to do is we want to just take the concepts that we've developed so far and extend them into 2 and or 3 dimensions. And so we'll begin with this lecture, which will be position, velocity, and acceleration vector. So just extending those quantities that we've looked at already into multiple dimensions. So let's go ahead and jump into it. We'll call this section 2.1 position, velocity, and acceleration vectors. Okay, and so to describe the motion of a particle in space, we first have to begin by describing its position. And so we'll use the position vector for that. And there's different notations you will find or come across if you look in various places, but we're going to use R as to denote our position vector. So the position vector, R, is a vector that you can think of as going from the origin of your chosen coordinate system to wherever your object is located in 3-dimensional space. So the position vector R is a vector that goes from the origin of the coordinate system to the point, and then we'll just use P here. So let's draw a little example here. So I've got my XYZ coordinate system, and so I've got 0, 0, 0 here. And let's say I've got an object P located somewhere in this space, and let's just say that P is located like this. Okay, so and we'll say this is X, this is Y, and that is Z. And so obviously I'm off center on the X-axis, I'm off center on the Y-axis, and I'm clearly extended above the XY plane, so I'm off center in the Z-axis. And so this would be my position here. We'll just call it X, Y, Z. Okay, and so we could denote this using the position vector as R equals, there's different ways to denote it. You could write it like this, X, Y, Z as an order triple, or a way that I think is somewhat more common in physics would be using this kind of notation where we say X I hat plus Y J hat plus K Z hat. And here, this is I, J, and K are unit vectors, where I, J, and K are the unit vectors, right? So just to refresh our memory on this I would be 1, 0, 0, J would be equal to 0, 1, 0, and K hat is equal to 0, 0, 1, right? Okay. So this would be the simplest way to kind of think of the position of an object in a coordinate system using a position vector like R. R is equal to the X component times I hat plus the Y component times J hat plus the Z component times Z hat. Okay. Now, as a particle moves through space, its position vector is going to change. So let's kind of drop out of 3D and jump to a 2D version instead. It just gets a little difficult to draw some of these things, right? And so let's just say that my vector is positioned like this, right? So this would be my R1. Okay, so I start up here. And then let's say the object moves down to this position, P2, and so my position vector is going to change, right? Like so. So as the particle moves through space from P1 to P2, its position vector changes from R1 to R2. Okay, and so given a certain time interval, we can calculate the displacement. So we'll say, given an interval of time, and we'll just denote that as delta t, the particle's displacement is delta r. And that's going to be a vector too, isn't it? It's going to be basically the difference between r2 and r1. So r2 minus r1, which if you think about what r2 and r1 are, in this case in two-dimensional space, this is just going to be equal to x2 minus x1 times I hat plus y2 minus y1 times j hat. Okay, and so there's your displacement vector. So if I know the position vector at over an interval of time at the beginning and the end of the interval, I can calculate the displacement, and given the displacement, I can calculate the average velocity. Right, and so we can define the average velocity during the interval in the same way as before, except we just replace everything with vectors. Right, so the average velocity is just going to be equal to the displacement, which in this case is r2 minus r1, divided by the time, t2 minus t1. Right, and you could denote this again using delta r over delta t. Now, important to note here that t1 and t2 are you should think of them as scalars in this context, right? So they're really, t2 might be 5 seconds, t1 might be 1 second. So really, t2 minus t1 is the scalar 1/4. That's kind of the way to think about it in the context of these vectors. They're not vectors. The time elements are not vectors. They are just scalars. Okay, let's see an example. Pull some of this together. So let's find the average velocity of a particle that moves from r1 equal to 1, 0, 3 to r2 equal 115 over the 3-second interval from t2 equals 5 seconds and t1 equals 2 seconds. Okay. All right, so it'll probably take longer to write the question than it does to actually calculate this. So the average velocity is equal to r2 minus r1 over t2 minus t1, right? So the displacement divided by the time, right? And so we can think of this as just vectors, 115 minus 103 divided by 5 seconds minus 2 seconds. Okay, and so what do we get here? Well, it's totally fine to think of this in this sort of format, but I do think that in physics, and this would be like the way you would want to kind of think of it if this was like a linear algebra course. But in physics, it is more common to write this using the IJK notation. So kind of another way to write this would be I plus j plus 5k minus I plus 3k, right, all over 5 seconds minus 2 seconds, right? And so you wouldn't have to go through this. I just want to emphasize that this notation can be easily converted to this notation, just by recognizing this is I, this is j, this is k, and so on. So then how would we do the math here? Well, we would subtract the I components, we would subtract the j components, we would subtract the k components. And so what do we get? We get 1 minus 1i plus 1 minus 0 j plus 5 minus 3k. And all of that divided by 3 seconds. And so this is really just like 1/3 of, let's see, j plus 2k. Okay, and this would be meters per second. Right, and so really the way to deal with the units here is to put the units on the actual components. And so the best way to frame this up would be to say 1/3 meters per second in the J direction plus 2/3 meters per second in the K direction. Okay. All right, so that's the answer. This would be the average velocity over this interval, hypothetical interval, this example. Okay. Pretty straightforward. It's just you have to remember your vector arithmetic. You have to remember how to write vectors, how to add and subtract them. But I do think that's pretty straightforward stuff. So given how we've defined average velocity, instantaneous velocity is going to follow in the same manner as it followed in this example of straight line motion. So it follows that instantaneous velocity is defined as, so again, it's a vector, and it's equal to the limit as delta t goes to 0 of the position vector divided by the time displacement, the time change. Right, and so in the limit, this becomes the derivative of position. Just like that. Just like before. Okay, just like before. Except the only difference between what we're doing now and what we did before was that previously we were talking about numbers, just simple numbers. Now everything is a vector. Right, so now my numerator here is a vector, and my denominator is, well, just time. Okay, very good. Now, when we're talking, because we've moved from straight line motion to 2 or 3 dimensional motion, the vector, the velocity vector, is going to have 2 different aspects to it, because all vectors have these aspects, magnitude and direction. Right, so velocity as a vector has both magnitude and direction. Right, that's the case with all vectors, right? And so we've specifically moved into space now, and so we have to start thinking of our velocity as having magnitude and direction, not merely being a synonym for speed. Right, so the magnitude of v, of the velocity vector, at any instant, the magnitude of the velocity vector at any instant really is the speed of the particle at that instant. Right? So the magnitude of the velocity vector is basically the same as the speed of the particle. Okay, and then contrast that with the direction. The direction of the velocity vector v at any instant is the same as the direction in which the particle is moving at that instant. The direction of the velocity vector at any instant is the same as the direction in which the particle is moving at that instant. Right, so the velocity vector will always be, you can think of it as always being tangent to the path at a given point. So let me try to draw a picture here. Sometimes these pictures come off great, sometimes they're terrible, but I'm going to give it a shot here. So I've got my XYZ coordinate system, and I'm just going to kind of lightly tap in a path here. So let's say this is my path, right? And so let's say the point I'm interested in is right here, right? So if this is my P1, then my velocity vector would look like this at that path, at that point. Right, now let's say this is now my point of interest. My velocity, so this would be my V1. My velocity vector here would be more like this. Okay, and so the idea that this picture is trying to get across here is that the direction of the velocity vector is always tangent to the path, right? So the direction of V at point P is tangent to the path at point P. Right, so hopefully you've seen some calculus, you know what I mean by tangent. The idea is that if we think of the path as this curve in space, then the velocity vector is going to touch that path at a single point, namely P1 in this instance. It's going to touch it at just that point. It's going to be equal to the slope of the path at that point. Okay, very good. So that's the idea. So you've got the magnitude of V, which we know is a scalar, and we'll talk about how to calculate it in a moment. And then we've got the direction of the velocity. Now the magnitude tells us the speed of the particle at a given point, and the direction of V gives us the direction of the path. Gives us basically the slope and inclination of the path at the same point. Okay. All right, so you've got these two pieces of velocity now, whereas before everything was on a straight line. There was no real direction component. Everything was just magnitude. But now we're truly using vectors, and we have to think about both the direction of the velocity and also the magnitude. Okay, very good. All right, so moving on, it's usually easiest to calculate instantaneous velocity using the components, right? So what we can do, so we'll say we usually use components of position to calculate velocity. Okay, so for any displacement, so given a delta r, right? So given any displacement, the changes delta x, delta y, and delta z, if we're in 3 dimensions, for this displacement delta r, the changes delta x, delta y, delta z are in the 3 coordinates of r are the components of delta r. So these are the components of delta r. Okay, and so if I'm given a position, if I'm given a displacement, I can use the components of the displacement vector to calculate the velocity. So v of x, the x component of the velocity, is equal to the derivative of the x component of position. And the y component of velocity is equal to the y component, the derivative of the y component of position. And of course, the z component of velocity is equal to the derivative of the z component of position. Okay. And so, in fact, I mean, you can think of it also being the case that the x component of velocity is really just the same as the instantaneous velocity for straight line motion, right? So we can write things like this. So v, the velocity vector, is equal to the derivative of the position vector, right? Which is just equal to d dt of the, whatever I plus j plus k is, right? So you could write it like that. You could also think of it like this: dx dti plus dy dtj plus dz dtk. Right, so you can write it like this. So this would be the velocity vector. So you've got your ijk position vector. If you differentiate the components, so there's components out here. Sorry, I should write xi, yj, zk. All right, if I take the derivative of x, that gets me the velocity, x component for velocity. If I take the derivative of y in position, that gives me the y coordinate of the velocity vector, right? So I can separately differentiate these components, and well, that makes your life a whole lot easier. If you think that's, kind of how vector calculus works. If you've been through calculus 3, you've certainly seen this. Now, what about the magnitude? Well, the magnitude of the instantaneous velocity is given by, bet you can guess, it's equal to just the norm of the velocity vector. So it's equal to that, and we sometimes just denote it as v. And it's equal to basically the x component of velocity squared plus the y component of velocity squared plus the z component of velocity squared. Take the square root. Just like that. And then, of course, if we want to know something about the direction of the instantaneous velocity, we can think of it as an angle off of the x-axis. So we can also think of the direction of the instantaneous velocity, v, is given by the angle alpha in tangent of alpha equals the y component of velocity divided by the x component of velocity. And this is the case of 2D. And so sometimes this is important, right? If you think about, I'm in the xy axis here. So I'm in the xy plane. Then, I've got some path here, and my velocity vector looks like this maybe, right? Well, my velocity vector is going to have an x component, and it's going to have a y component. All right. And then this angle alpha is really this piece here. Right, it's really that lift off of the x component of the velocity, and that tells you the direction. It's one measure of the direction. There are other ways to think about it too, depending on the scenario. Okay, so we can think of direction in that way as well. All right, we've done a lot of things. Let's take a look at an example. Let's get some actual numbers out here, maybe some expressions, and mess with these things. So I'm gonna just like previously, I'm gonna try to write the whole thing out, and then give you a chance to solve the problem on your own, give it a try, and then we'll go through it. So, an object is moving in two-dimensional space. Its coordinates at time t are given by, so we've got an x coordinate that's equal to 2 meters minus 0.25 meters per second squared times t squared, and its y component is equal to 1 meter per second times t plus 0.025 meters per second cubed times t cubed. Okay, so I've got this I've got these pair of expressions for the position of an object at time t. Okay, right, so if I want to know where the object is at in 2D space at 3 seconds into its trajectory, I can just drop in 3 seconds into this expression. It'll give me the x coordinate and the y coordinate. Okay, so this is pretty straightforward. So then what are we interested in? Let's 3 parts to this. Let's find the object's coordinates. Find the object's coordinates and its distance from the origin at t equals 2.0 seconds. Okay, so that's just a straightforward thing. And second, let's find its displacement and average velocity between t equals 0.0 seconds and t equals 2.0 seconds, right? Okay, and then thirdly, let's derive an expression. Let's derive an expression for its instantaneous velocity. Okay. All right, so there's the 3 parts of it. So again, I would recommend that you pause the video here and take a stab at solving this problem. I think it's definitely doable, but a good idea to try to do it yourself, just because it'll help reinforce the concepts versus if I just do it for you, and you won't necessarily have to work as hard. Okay, so I'll just assume you've taken a stab at it. Let's go ahead and solve this problem. So for part A, we're interested in, what are we interested in there? We're interested in the object's coordinates and its distance from the origin at t equals 2 seconds. So let's see, at time t equals 2.0 seconds, where are we at here? Well, x of 2.0 seconds is equal to 2.0 meters minus 0.25 meters per second squared times 2.0 seconds squared. Okay, you plug all of that in. It's a straightforward plug and chug, and you get that the x coordinate is 1.0 meters. Okay, now what about the y coordinate at the same time? Well, it's the same exercise, different expression though. So y at 2 seconds is equal to 1.0 meters per second times 2.0 seconds plus 0.025 meters per second cubed times 2.0 seconds cubed. Okay, and again, just crunch all that through your calculator and you'll get 2.2 meters. Okay, and so the particle is at, let's see, so the position would be, the r vector would be r of 2.0 seconds is equal to 1 meter I hat plus 2.2 meters j hat. So that's the position of the particle at 2 seconds. All right, perfect. Right, and then you could identify the displacement from the origin, the distance from the origin, by just looking at this. The distance is equal to 1 meter squared plus 2.2 meters squared, and take the square root, right? And I'll let you figure out what that is. That would be the distance from the origin. Excellent. Part B. What's part B? Well, for part B, we're looking for the displacement and the average velocity between t equals 0 and t equals 2 seconds. Okay, so to find the displacement and the average velocity, we need to express the position vector as a function of time. So r of t is equal to, let's write this all out. Now, this is not always the best way to represent this, but I'm going to do this just so you can see that this really truly is a vector. right? So you have 2.0 meters plus, or sorry, minus, let me just do this on another line here. So R of t would be equal to 2.0 meters minus 0.25 meters per second squared times t squared, and that's your I component, your x component, and then plus, and then it's 1 meter per second times t plus 0.025 meters per second cubed times t cubed, and that's your j component. So this here is your x component, and this is your y component. Okay. And so where were we at t equals 0 seconds? We may have been at the origin, but we may not have. Let's go ahead and see. So at t equals 0 seconds, we'll say the position vector at time 0 would be, now you're going to plug in a 0 here, and so that's going to 0 out, and that's just going to be 2 meters. So I'm going to have 2.0 meters I hat. Now what about my j hat? Well, this will 0 out and that'll 0 out, so I'm going to have 0 meters j hat. So that's my position at t equals 0. Now what about at t equals 2 seconds? Well, that's the one we just did, isn't it? Right, so R2, here I'm using R0 meaning t equals 0, and R2 meaning t equals 2. So at t equals 2 seconds, my position we just found was 1.0 meters plus 2.2 meters. Right, and so I hat, j hat, respectively. And so what's my displacement? Well, delta r is going to be equal to R2 minus R0 in this case. Right, so R2 minus R0. And so that's going to be 1.0 meter minus 2.0 meter I hat plus, and then it's 2.2 meters minus 0.0 meters j hat. Okay, and so I can see that my displacement is negative 1 meter in the x direction plus 2.2 meters in the j direction, or the y direction. All right, and what's my average? So that's my displacement. So what's my average velocity over that same time interval? So v average is equal to the delta r over the time interval, right? And so I know my delta r, just calculate, it's going to be negative 1 meter I hat plus 2.2 meters j hat divided by 2 seconds minus 0 seconds, right? And so it's going to be equal to basically 1/2 of the displacement, isn't it? So it'll be equal to, let's see, negative 0.5 meters per second I hat plus 1.1 meters per second j hat. There we go. Right, so I've got my displacement, and then I've got my average velocity. Right, so it's just half because it was a 2-second interval. Okay. Very good. And then part C, what were we interested in part C? Well, we wanted to derive an expression for the instantaneous velocity. All right, so part C, what are we interested in here? The instantaneous velocity. So the instantaneous velocity is, well, we need to know, I don't know why I put an X there. The instantaneous velocity is equal to the derivative of the position, right? So I have to differentiate the position vector, right? And I'm going to kind of I'm going to use all the notation that I can in here just so you can see how all of this flows. All right, so I've got, that's going to be ddt of, I'm going to write out the position vector, 2 meters minus 0.25 meters per second squared t squared I hat plus 1 meter per second times t plus 0.025 meters per second cubed, t cubed, j. Okay, so I've got the derivative there. All right, and then what the whole point that I was making earlier is that the derivative, when you differentiate a vector like this, you really just need to differentiate the components, right? And so this would be equal to ddt of 2 meters minus 0.25 meters per second squared, t squared, that's your I hat, plus separately the derivative of the y component, 1 meter per second t plus 0.025 meters per second cubed, t cubed. Okay. Right, and can we differentiate all of this? You bet. So this is a constant, so it's the derivative is going to be 0. Here we've got 0.25 times t squared, so we're going to end up writing 0.5. And so this will be negative 0.50 t, and that's the I hat. And then plus, now over here I've got 1 meter per second times t, so we're going to, if we differentiate that with respect to t, we just get 1 meter per second. And then what do we get here? This will be, that's cubed. So it'll be basically 3 times that, right? So it'll be 0.075 t squared. Sorry, meters per second cubed t squared. Okay. And that, so I left the units off here. Let me rewrite this with the units. This should be negative 0.5, and this is meters per second squared times t times I hat plus, I want to make sure to leave the units on, so 1 meter per second plus 0.075 meters per second cubed, and that's t squared j hat. Very good. Okay, so that is an expression. So this would be the instantaneous velocity. Now notice when we plug in any value for t, we're going to get units that are meters per second, right? So if I plug in 3 seconds, I'll have one of the seconds will cancel, meters per second. If I plug in 1 second here, I'm going to get seconds squared over seconds cubed, so I'll retain the meters per second, right? So it's very important to kind of get used to that. If this is your first, if this is your first time messing around with, you know, some of these physics concepts, then just make sure you're understanding how the units are kind of taking care of one another. So, okay. Very good. So that's a good example, a good introduction to position and velocity. Let's next turn to the acceleration vector. So just like with average velocity, we can define average acceleration over an interval, right? So just like with average velocity, we can define average acceleration as, so average acceleration is really going to be the change in the velocity vector, right? We just talked about the velocity vector. It's going to be the change in the velocity vector over an interval of time. So you can think of it like v2 minus v1, those are vectors, divided by t2 minus t1. Or it really is just delta v, v being a vector, divided by delta t, right? And so we know how this story is going to go. We know what comes next. Really, instantaneous acceleration is going to be then the limit as delta t goes to 0. So instantaneous acceleration is then going to be equal to the limit as delta t goes to 0 of delta v over delta t, which we also know as the derivative of v with respect to t. Okay, so no surprises there. That's exactly what we would expect to see. All right. So a couple of things about acceleration that are important. I mean, I really think acceleration really does kind of govern the way things move in our world. There are subtle differences between velocity and acceleration that you have to be very careful to distinguish early on. So whereas the velocity vector was seen to be always tangent to the path of the particle, that's not the case with acceleration, right? So whereas the velocity vector is always tangent to the path of the particle, this is not the case for acceleration. Now, hopefully that's straightforward, right? Because velocity is the derivative of position, right? And so the derivative is always tangent to the function's curve. Acceleration is the second derivative of position, so it's not going to be tangent to the curve, right? So for acceleration, the acceleration vector always points towards the concave side of a curved path, right? So if I've got a path, right, this is the particle's path, right? It's moving along this path. The velocity vector is going to look like this. It's going to be tangent, right? Meaning it's touching the path at just this one point. The acceleration vector is not going to be tangent to this curved path. Instead, it's going to look something like this. It's going to point off the path in the direction of the curvature of the path, right? So you can think of this as this path is concave, right? So the acceleration is going to point in the direction, it's going to point towards the concave side of the curved path. So acceleration always points towards the concave side of a curved path. Okay, so it's always going to point towards the concave side of a curved path. Okay, and so if you think about this for a moment, what you'll probably come to grips with is the fact that a particle, when a particle is moving on a curved path, it always has non-zero acceleration. So when a particle is moving on a curved, that's a U, curved path, it always has non-zero acceleration. Now, this is true even if the particle's speed is constant, right? So we tend to think in the one-dimensional case, if an object's speed is constant, then it has no acceleration. But in the two or three-dimensional space, even if a particle has constant speed, if it's on a curved path, its acceleration is non-zero, right? So if my velocity is like this, but I'm changing direction, then my acceleration is non-zero, right? So even when it has constant speed. Very important, right? This is a tricky concept sometimes to get. So I guess one way to kind of remember it or to think about it is think of the forces that you feel, like if you're in the backseat of a car that's going around a corner. Even if the speed of the car isn't changing, right, as you go around the corner, even if the speed is constant, you still feel the force of the acceleration of your velocity vector changing, right? Your velocity vector is shifting direction, and that's an acceleration, right? And so you can kind of remember it in that sense. Like if you're going 20 miles an hour and you suddenly start curving, then you feel a force, you feel an acceleration towards the outside of the curvature in that case. So, okay, now each component of the acceleration vector is going to, just like before, be the derivative of the corresponding component of the velocity vector. So each component of the acceleration vector is the derivative of the corresponding component of the velocity vector, right? So AX, for the X component of acceleration, is equal to the derivative of the X component of velocity. And the Y component of acceleration is equal to the derivative of the Y component of velocity. And of course, the same for Z. The Z component of acceleration is equal to the derivative of the Z component of velocity. Okay. Right, and so we could say that the acceleration vector, is equal to dvx over dt I hat plus dvy over dt j hat plus dvz over dt k hat. Right? So that's just those are just the derivative of velocity, right? It's also true that it would be the second derivative of position. Right? So d squared r x dt squared, and d squared ry dt squared, and d squared rz dt squared, right? So this is the second derivative of position. That's also acceleration, just like before, right? In the straight line case, we saw that if you start with the position function, you differentiate it twice, you get the acceleration function. Same idea. Same idea. Now we're just dealing with vectors. Okay, so another item that's very important to develop some sense of with regard to acceleration vector is the idea of breaking the it's often useful to describe the acceleration of an object in terms of components that are parallel and perpendicular to the velocity, right? So let me give you an example of how this works. So let me just write this down. So it is often useful to describe the acceleration of an object in terms of components that are parallel and perpendicular to the velocity. Now, why is this? Okay, I'm going to give you kind of two examples here. Well, first let's just draw the situation. What am I even talking about here? So I've got a path. Okay, so I've got some path, and I've got my particle on that path. Now I know that the velocity of my particle is a vector that's tangent to the path. Now it turns out, and then my acceleration, we just learned that my acceleration is going to be off the path. It's not going to be tangent to the path. It's going to be in the direction of the concave side of the path. So it'll look like this. Now, it turns out that my acceleration can be broken down into two pieces. First, there's this piece, which is in the direction of the velocity, and I'm going to call that A parallel. So A parallel. So the parallel acceleration. So this is the part of the acceleration that's in the direction of velocity. And then there's a perp, which I'll denote again with an A, but instead of parallel lines, I'll put a perpendicular line. So this would be A perpendicular. This is the perpendicular acceleration. Okay. Now, notice the sum of these two is the acceleration. So the acceleration is equal to A parallel plus A perpendicular. Okay. So the kind of the takeaway idea here is that some of the acceleration is in the direction of the velocity, and some of the acceleration is in the direction normal to velocity, meaning perpendicular to velocity. Now, in some cases, all of the acceleration is in the direction of velocity, and in some cases, none of the acceleration is in the direction of velocity. Right? And so let's take a look at two specific cases, basically those two extreme cases, and see what it looks like. So let's consider two cases. Okay, case one, we're going to say the acceleration is, in this case, all parallel to v. Right, so the acceleration is 100% parallel to the velocity. Right, so what does that look like? Well, I've got some velocity vector here. Okay, and I've got acceleration in the exact same direction. Right, so if this is my initial velocity, what's my velocity after some time interval going to look like? Well, it's going to be the same direction, identical direction, but just longer. Right, and basically that's going to be just all due to the fact that the acceleration is in the same direction, and the only thing that's going to happen is my velocity is going to increase. The direction will stay exactly the same, the velocity, the magnitude will increase. So here, direction stays the same, right? Because there's no perpendicular acceleration, so that means none of the acceleration is going into changing my direction. Hence, I will not change direction. So here the direction stays the same, but the magnitude changes. Right? So if all of the acceleration is in this exact same direction, it's parallel to the velocity, then that means I'm speeding up. I'm staying the course. I'm not changing direction. I'm just increasing my speed. Right? So in this case, we would say that the speed is increasing, but the direction is staying the same. Okay, so this is case one. Okay, now usually when people think about acceleration, this is the case they think of. They tend to think of, oh, that when I accelerate, my speed changes. That's sort of the naive interpretation, right? Case two is the case that nobody ever thinks of in a naive way, like if you're not in physics class. Case two says what? Well, in case two, I start with some velocity. Okay. And in case two, my acceleration is perpendicular. Right? So it's perpendicular to the velocity. So if the velocity is in this direction, my acceleration is in that direction. Right? It's perpendicular, 90 degrees. Okay. And so what's going to happen is my velocity magnitude, the magnitude of my velocity is not going to change. Right? Notice V1 and V2 are drawn such that they have the same length, right? So my speed is not going to change. My magnitude is not going to change. What's going to change is my direction. Sorry, that's delta V. The car didn't change speed, it just changed direction. If you're barreling down the freeway and you go around a corner, your cruise is set at 65, the magnitude doesn't change, but your direction changes. And then in those instances, that's what's happening is your acceleration is completely perpendicular to the velocity of the car. Okay, so in this case, A is perpendicular to V. Okay, A is perpendicular to V. And so delta V is a vector nearly perpendicular to V1, right? And so here delta V, you can see this is not going to be perfectly perpendicular. The acceleration is perfectly perpendicular, but the change of velocity won't be quite, right, just because of the way that the physics works out. But the acceleration here is working to 100% change direction. It is not changing the magnitude. It's not speeding the car up or slowing the car down. It is changing the car's direction. Okay. All right, very good. So let's summarize those 2 points. Okay, so to summarize, this is very important. You'll need to be able to kind of think about these 2 pieces of acceleration whenever we're trying to break down like the motion of a particle. So to summarize, we say that when A is parallel to V, when the acceleration is parallel to the velocity, it results in an increase in the speed. It results in an increase to the speed of the object and no change to the direction. Okay, so if the acceleration is parallel to V, it's just purely adding speed to the object and doing nothing to the direction. And conversely, when A is perpendicular, to V, it results in a change in direction. It results in a change in direction, but no change in speed. Okay. All right. Let's do a couple of examples, kind of break this down a little bit. This is a super important concept. So I'm just going to draw some pictures here. So let's start with, here's my path, right? And with my point of interest is here. My velocity is in this direction, tangent to the path at the point of interest. Okay. Now I'm going to just draw let me draw a perpendicular indicator here. So this is just my way of drawing in this is just the perpendicular line to the velocity, right? So my velocity goes here. This dashed line is forms a 90-degree angle with the velocity. Now, if my acceleration is perfectly aligned with this perpendicular, what's gonna be the situation? What's happening to the speed of the car? In this case, the velocity, the speed, the magnitude of the velocity is constant. So this is constant speed, right? So here we would say that the acceleration is equal to the perpendicular acceleration. And therefore, I guess we would be implying that the parallel acceleration is equal to 0. There's no parallel component to the acceleration. All of the acceleration is committed to changing the direction of the velocity vector, not changing the magnitude, right? So here, what you end up with is constant speed. This is the example of us barreling down the freeway with the cruise control set, going around a gentle curve. We are technically undergoing acceleration, but our speed is constant. Okay, now what about this? What about a path that looks like this again, right? And I've got a velocity, a point of interest, and my velocity vector looks like this. And then once again, I'm gonna draw my perpendicular ray here, right? So again, this is the dashed line is perpendicular, it's at a right angle to the velocity vector, which is tangent to the path. Now, what happens if my acceleration looks more like this? Now, what's happening here? In this case, my speed is going to be increasing. My speed here is increasing, right? So in this case, A parallel is not equal to 0. Okay, it's not equal to 0, and A parallel is in the direction of V. Can we see that? Well, if we were to break this down, so I've obviously got A perp is here, and then this would be A parallel, right? Which is in the direction of velocity, right? Here's velocity, here's A parallel. Okay, so A parallel is in the direction of the velocity, right? And so what that means is whenever you're accelerating in the direction of velocity, that means you're speeding up, right? So I've got I have some piece of this acceleration that's in the direction of the velocity, therefore this object particle is increasing in speed. So this is like me going around the corner on the freeway, and instead of having the cruise control on, I've got the car floored, right? So I'm accelerating. I've got my pedal to the metal, the foot to the floor, and I'm accelerating around the curve. So there's an acceleration that's, accelerating me by changing my direction. It's also accelerating me by increasing the magnitude of my velocity. And then lastly here, for this example, again, same path, particles here, there's my velocity, and again I've got my perpendicular. But in this case, let's say my acceleration is slightly back like this. So if my acceleration looks like that, what's going on? What's happening in this case? Well, in this case, my speed is decreasing. So again here, the parallel component of acceleration is non-zero, and the parallel component of acceleration is in the opposite direction of V. Can we see that? Well, again, here's this piece here would be a perpendicular, right? And then so to get from the point to the tip of my acceleration vector, I have to go this direction, and then I have to go this direction, don't I? So A parallel is in the opposite direction, namely this direction, of my velocity vector, which is going this way, right? And so what's happening here? Well, my speed is decreasing. I'm on the freeway, I'm going around a corner, and I'm applying the brake subtly, right? So my car is slowing down and changing direction. So I'm accelerating in such a way that the magnitude of my velocity is decreasing. Very good. All right, so it's super important to be thinking about acceleration as not just something that makes you speed up, but also something that can make you slow up, and also something that can make you change direction. All right, so those are all pieces of the acceleration picture. Okay, let's do one more example just really quickly, just to kind of drive this concept home. So in this is an example, kind of a classic example. You got a skier moving along a ski jump ramp. A skier is moving along a ski jump ramp. Okay, and so we know, so you go down this big hill, and then the hill kind of flattens out, and then you jump, right? Looks a bit like that, right? So I'm a skier, I'm just racing down this hill, and then I get to the bottom, and it flattens out, and then I shoot off this thing, and I go, flying into the air. Now the ramp is straight, so let's mark off a couple spots here. So we'll start up here with A, and then we'll put something here called B, and then something right about here called C. Now between A and C, the ramp is perfectly straight. So the ramp is perfectly straight between A and C. Okay, and it's curved from C onward. It is curved from C onward. Okay, so let's see if we can draw in the direction of the acceleration vectors, and not precisely, but like, can we just reason about what must be happening at each of these things? So A and B, the skier is going to be moving perfectly down here in a straight line, no curve. So that means acceleration is going to be 100% in the direction of the velocity, right? We can't have a perpendicular acceleration if we're not changing directions. So we're not changing directions, hence all of our acceleration is parallel to the velocity. Now at C, we'll not worry about that as a point, but let's think of it as a change point in the track. So at C, the track starts to curve perfectly straight up till C, and then it starts curving. So let's lay in a couple points here. We'll call it D, E, and F. What's going on here? Let's take each of these separately. So what about at D? So at D, the skier has just passed C and is starting to move along a curved path. So here the skier is moving along a curved path, right? So what that means then, that implies that the perpendicular acceleration is now no longer zero, right? Some portion of the acceleration is going into changing the direction of the skier, right? And so let's draw like a little miniature here. So if it looks like this, and this is my D, then my perpendicular would be like this. Okay, so that's like a 90-degree angle. Now I'm still going downhill here, right? I'm still going downhill. So my acceleration would be something like this, wouldn't it? Instead of being perfectly in the direction of velocity, here's my velocity vector. My acceleration is going to be a little bit, some portion of it is going to be lifted off of out of the direction of velocity, because I'm changing directions, right? And my acceleration is always towards the concave side of the curvature of my path, right? So it's going to look something like this. Okay. What about at E? Well, at E, the skiers, so really E is meant to be at the bottom, right? So the velocity would be like this, right? So at E, it's really the bottom of the ramp. My velocity looks like that, and so my perpendicular would be like this, and really my velocity is instantaneously unchanging here at the bottom, right at the bottom of the ramp. I haven't started going uphill yet, and I've just finished going downhill, so I'm no longer picking up speed due to gravity. I'm not yet being affected by gravity, right? So what's really happening here is my acceleration is 100% in the direction of that's perpendicular to velocity. So we would say here that the skier's speed is instantaneously unchanging, not at rest, unchanging, is instantaneously unchanging. Okay. So all of the acceleration is normal to the path. Right? So all of the acceleration is normal to the path. So what we would say here is that the acceleration is equal to the perpendicular acceleration, and a parallel is 0. That's what's happening at E. And then at F, what's going on at F? Well, we've started going uphill, haven't we, right? So now my velocity is heading that direction. I'm uphill. There's going to obviously be some in gravity's role in this whole situation has reversed. At F, the acceleration, so let's draw a picture here. So maybe it looks like this. I'm at this point now. My velocity is headed up like this now, and my perpendicular is like this, right? At F, the acceleration has a perpendicular component and a parallel component, just like it did at D, right? But in this case, the parallel component is opposite the direction of the motion. So my acceleration would be more like in this direction, wouldn't it? Right? Which means this is my normal component, my perpendicular component, and this would be my parallel component. Now notice the parallel component is opposite, in the opposite direction as the velocity, right? So here, the skier's speed is decreasing, right? And you could just think of that from a common sense standpoint as, hey, he's going uphill now, right? This guy's going uphill, so gravity's holding on to him, pulling against his velocity, right? And so in this case, perpendicular velocity is non-zero, parallel velocity is non-zero, but parallel velocity is in the parallel acceleration is in the opposite direction as velocity, right? So the skier is slowing down and still turning, and also still turning. Okay, very good. So that I think is a good spot to end here. It was a little bit longer lecture than is typical, but next time we get together, we will begin talking about projectile motion, which is a super interesting, super intuitive. I think it all kind of starts to come together with projectile motion. So we'll get into that next time. All right, take care.